In this video, we're going to talk about graphing an ellipse, which is a shape that is like a circle in a way, but kind of stretched. And the points on the ellipse have distances from two focuses, or foci, that is constant. So the distance from this focus down to this point and over, that distance is the same as from here to the point and back. We have two axes. We have a major axis, which is the longest distance across the ellipse, and the perpendicular bisector of that is our minor axis, and those two lengths are real important. We're going to be talking about the distance of half of those from the center out to this vertex out here is the semi-major axis. The distance from this center to the vertex up top or down below is called the semi-minor axis. When we look at the equation, we have x minus h squared plus y minus k squared, where h and k are the coordinates of the center. And then if it's horizontally stretched, then the largest value a, which is the semi-major axis, right here. Let's try that again. So that is the semi-major axis, this distance here, out to the vertex, or which is the same as going out to here. So that's going to be the largest number. And the smaller number, the smaller two denominators is b, that's this semi-minor axis. Now, if the vertex is stretched, or the ellipse here is stretched in a vertical direction, then that a value will be under the y. Okay? So we'll see how that works. Let's take a look. And one more important distance is going to be this distance to the focus, and that's c here. Now, it turns out that a, the semi-major axis, is also the distance from this focus up to the top of the minor axis there, and b is what we call the semi-minor axis. We talked about that. And again, c is the focal distance, and it turns out that we get our nice right triangle here, and in this right triangle, a is the hypotenuse. So because of the Pythagorean theorem, we know that the hypotenuse squared equals the two legs squared added together. Okay? Now that doesn't look like our normal Pythagorean theorem, but keep in mind a is the longest distance of all three here, so that's got to be by itself. Let's try an example here. So here we have an equation of an ellipse. You know it's going to be an ellipse because we're adding, and we have 1. It's got to be equal to 1. Never going to be equal to a number. If it is equal to some other number, you got to divide through. And we have our standard form, x plus something squared, y plus something squared. Okay, and let's see what we got. So the semi-major axis, that's a. Well, that's the square root of the largest denominator. So in this case, a is the square root of 64, which is 8. All right, the semi-minor axis is the square root of the smallest denominator, and so that's going to be b. And so the square root of 16 gives us 4. The coordinates of the center come from these values, h and k. Remember, standard form is x minus h, so that's going to give us an h value of -1, because it's like minus -1, and the k value is going to be 3. So this is moved up 3, like a transformation there. All right, that's enough to graph it there. So let's get our graph. We know our vertex is at -1, 3. Let's go with a scale of 1 here. All right, so we've got our center over here. Now we know the a distance is a semi-major axis. That's the longest distance that it's going to be stretched. And notice that it's under the y. That's important, because the largest number is under the y. This is actually going to be stretched vertically. So the major axis is going to go in the vertical direction. And it looks like we're going to go off the charts here. That's okay. So we're going to go up 8 and down 8. All right. So we're going to count up. That'll put us up here actually at 11. which is off our scale here. That's all right. And then we're going to go down 8. Let's put it down at -5 down here. Okay. And then we're going to go to the right 4 and to the left 4 from the center. So from the center, we're going to go to the right 4, which should put us right out here. Oops. Right out here, approximately. And to the left 4, 1, 2, 3, 4. Puts us right there. So now we've got these points, and that's enough there to get a sketch of our ellipse. Let's see how I'm going to round it off. Something about like that. Okay. And our axes once again going from here. There's our there's our major axis. And our minor axis is going across here. All right. So now we need to find the focal distance. Where is the two foci on this? Well, we know our relationship here is a squared equals b squared plus c squared. Or if you solve this for c with a little bit of algebra here, we can get c equals the square root of a squared minus b squared. Okay, so that's a useful form. So let's go ahead and try that. The square root of a squared, that's 8 squared, minus b squared, which is 4 squared. And actually, we're doing a little bit of extra work here because where do we find a squared and b squared? Well, that's these values here. There's a squared, there's b squared. Could have stole them right from there. So we got 64 minus 16, and that's going to be the square root of 48, which simplified, if we pull a 16 out of there, is 4 root 3. All right, so we'll leave it like that. So there's our focal distance, 4 root 3. Okay. Now, the question is, what are the coordinates of the foci? Well, the focus are always on the major axis, so we're going to start from the center. We're going to go up the focal distance and down the focal distance. And so we're going to take -1, 3, that's our center, and we're going to go up and down. So the x-coordinate is going to be -1, the y-coordinate is going to be 3 plus 4 root 3, and same x-coordinate, but 3 minus 4 root 3. Now that's our exact answer there. If you want to compute an approximate there so we could graph it, then we can do that, about -1, 9.9. And so that is right up here. And -1, -3.9, that is going to be right down here. All right. So there's our two foci. Last but not least, what are the coordinates of our vertex? Well, we can take our center and we can go up and down the a value, add 3, subtract 3, and that's going to give us -1, sorry, not 3, add 8. 3 plus 8, 3 plus 8 is going to give us 11, and then we'll have -1, which is the x-coordinate, stayed the same, take 3 minus 8, and that's going to give us -5. And then we're going to go in the x direction. We're going to go 4 and -4. That's our b value. So we're going to change this by 4 and -4. So we're going to take -1 and add 4, and that gives us 3. The y value 3, this y value comes from here. Now we're going to take this and we're going to subtract 4 because that'll take us left. And -1 minus 4 is -5, and the y value stays the same. So here are the coordinates of the vertices. Now, since we were able to graph this, we could find that pretty easily. We could have just read here. We got -1, 11 is up there. -1, -5. We've got 3, 3. We've got -5, 3. And so there we can find all the important parts of an ellipse, which have lots of applications in science. And in general, these are special conic sections. So have fun. Good luck.